So we're very happy to have Andriana and Makridou here to tell us about quantum breaking and de Sitter. So take it away.
All right. First of all, thanks a lot for giving me the opportunity to present our work here. The talk is going to be based on this paper appeared on arXiv last November, together with our supervisor, Ralph Blumenhagen, and another student, Christian Kneisel. Sorry, can you see my slides properly?
Oh,
because
no,
it says that
I don't
sharing
think
is
so.
paused.
Let me.
I'll stop sharing and start again.
Yeah, try it again.
Okay.
I can see them now. Try mousing over.
Yeah.
No.
Okay, it worked
there we
finally.
Go. Cool.
All right,
Great.
Sorry for the delay then, and I can finally start. All right, the outline and at the same time motivation and goal for our talk was that there are several interrelations, let's say, between several bounds that appear concerning scalar potentials, positive scalar potentials, and in particular de Sitter. Some of them arise in the framework of the swampland, some of them arise with other physical motivation, let's say. And the main observation is that there exist links between most of them, but one particular link between the quantum breaking bound and the de Sitter conjecture was missing. So we wanted to study whether this link can be established. And to do so, we wanted to apply the quantum breaking approach to strings. And to do so, we studied the coarse grain approach to quantum breaking, and this led us to a thermal matter component which generalized to string thermodynamics, and then at the different limits of a finite temperature T, we study which limits we get very briefly. So let me start by explaining what the bounds that are involved in the first picture were. First of all, as you're all aware, the Swampland program relates those bounds arise from Swampland conjectures, which are conjectures that quantify which effective field theories can be UV completed to quantum gravity from those which don't and are do belong to the so-called Swampland. One very important among them is the so-called de Sitter Swampland conjecture, according to which the gradient of the potential over the potential itself has to be greater or equal to a positive constant of order 1 called C here. And this obviously forbids any de Sitter value. And let me clarify that I will not be talking about the refined de Sitter conjecture, which allows de Sitter value as long as there are tachyonic directions. And another relevant Swampland conjecture is the trans-Planckian censorship conjecture, which was a bit more physically motivated and states that sub-Planckian quantum fluctuations should remain quantum. And this actually is a slightly weaker conjecture in terms of the allowed potentials, and in principle allows for de Sitter as long as de Sitter is short-lived enough. And there is one particularly interesting case, and this is taking the asymptotic limit of the field space for positive potentials in TCC. And this leads to a bound of the same form as the de Sitter conjecture with an explicit prediction for this constancy, which is n-dependent, where n is the dimension of the space-time. So another physical reasoning that was suggested, let's say, to be behind these Swampland conjectures could be the no-eternal inflation principle, where in this recent paper, conditions for no eternal inflation were acquired by solving the Fokker-Planck equation. And for a linear potential in 4D, this was the condition that came up. And I will mostly focus on linear potentials because we will work in the framework of rolling and not the potentials that correspond to the refined Swampland conjecture. And in general, this bound can be generalized to this, this form, which can be defined in any dimension. And here is once again the number of space-time dimensions. And let me also say that we do not really care about what the value of this constancy here is. And any time we encounter some bound of this functional form, which has this n-2/4 scaling in the right-hand side. We will call it a no eternal inflation bound, even though it's not strictly, could be not strictly that. And in another recent paper, a very interesting relation of this no eternal inflation principle to TCC actually was uncovered, where a series of unstable de Sitter was studied. And in this setup, we had several metastable de Sitter, which went from one to another through a bubble non-perturbative membrane nucleation. And this setup was described by a dual EFT, and the Swampland conjectures that limited the form of this EFT scalar potential were studied through several Swampland conditions, and TCC was the most restrictive and actually gave the same bounds of this no eternal inflation type. So pretty much I have established the left-hand side of the figure I showed you in the first page, and let's move to the right-hand side. And this is the de Sitter quantum breaking approach, or in general quantum breaking, which was alternative description of gravity and aimed at taking into account quantum effects that cannot be usually seen in a semi-classical approach. And in particular for de Sitter was constructed as a coherent state of gravitons over Minkowski, and then the decoherence of this coherent state led to the so-called quantum breaking, which was the departure from the system from the initial classical description. And this time scale over it, which happened, was the so-called quantum break time. And this can be related to some inherent classical timescale of the system as the classical timescale over the quantum interaction strength. And for the specific case of de Sitter, it would give a timescale that scales like 1/h⁴. And now this quantum breaking approach made contact with the Swampland. And the main claim in this series of papers that were published shortly after the de Sitter conjecture, actually, the main claim was that quantum breaking should not occur. So some kind of classical procedure should take place and destroy de Sitter before we reach this time regime, or a moment in time where the quantum break time would settle in. And for a slow rolling potential, of course, this classical effect would just be rolling down the potential and can be written in terms of the Hubble parameter and a slow roll parameter. And then just by demanding that the classical decay happens before the quantum break time, we can extract the bound for the potential, which is of the exact same form as the non-eternal inflation type bound. And now the main question is, how can we make this bound stronger? So we want to reach the bound of the de Sitter-Swampland conjecture. And it is clear that then this right-hand side should become independent of the potential. This clearly happens for n = 2, but of course it's not very intuitive to say, okay, then we go to 2 dimensions and everything is solved. And also in view of the quantum break time, actually scaling of the quantum break time as 1/h would give the desired scaling here. And the first idea to generalize this quantum breaking approach to strings would be to construct some kind of coherent stage over a flat space, but instead of just gravitons, we could also include, let's say, in our description, string ingredients like Kaluza-Klein modes or higher form films or fields or whatever. But for us, this was not so trivial to do, and we chose a different way to describe quantum breaking. And this was the so-called coarse graining approach that was developed in a series of papers in 2016 and 2017 by Tommi Markkanen. And the idea was to study the de Sitter decoherence by tracing over states beyond the de Sitter horizon, since the observer standing at the center of the horizon does not have access to anything that's happening beyond the horizon. So according to this approach, one can write the band-stable vacuum as an entangled state in the static paths, and we choose the static paths because there we can immediately locate the horizon. And trace over the states beyond the horizon, get a reduced density matrix from that, and then use this reduced density matrix to compute any observables. And in the case of the energy momentum tensor, the interesting thing that becomes is that one acquires a new thermal matter component, which has an equation of state as radiation. And now this spoils effectively the initial Friedmann equations, and the Hubble parameter now stops being constant and becomes time dependent. And one can say that the jitter decays, and the decay time that arises during this decoherence approach can be interpreted as the quantum break time. And Markkanen actually computed this time in 2 and 4 dimensions, and therefore the result was precisely the same as in the approach by Dvali and collaborators. So we choose to extend this approach to a setup that is more suitable for strings. The initial setup concerned scalars in flat space with no mass and conformal coupling. This is not very usual in a string setting, so we try to have scalar fields with arbitrary mass, arbitrary space-time dimension, and we also set this coupling xi and here to 0. And then the procedure is quite straightforward, but a bit tedious at the same time. One has to be quite careful. The steps would be to just, first of all, find the equation of motion and the solutions to it in static coordinates. One would get 2 different solutions, one for inside the horizon, one for outside the horizon. Then we should construct continuous solutions across the horizon. Use these continuous solutions to describe, to define new modes, which will define our Banks-Davis vacuum. And in the end of this procedure, which was a direct generalization of what Markkanen did, one can write down the Banks-Davis vacuum as an entangled state between states inside the horizon and states outside the horizon. And then we trace over what we cannot see, we cannot access, and we get the following reduced density matrix. And then we compute pressure and energy density. Now this, in the case where we don't have the conformal coupling, actually is not so trivial. And also the fact that the mass is arbitrary does not get any special integer or half integer values, makes a full analytic approach a bit actually impossible. But we could have an analytic solutions which was written in terms of hypergeometric functions, etc., and study the limiting behavior of these solutions in the very large mass and very small mass compared to the Hubble scale limit. And what we found was the same in every situation, in odd or even dimensions or these different mass regimes. And it was that there was a flat space contribution for density and for the matter, which then when integrated scaled like h to the n. And what is important here is the scale. And even though we are not anymore in the conformal setting, so we expect some kind of curvature corrections to appear, the same h-dependent curvature corrections should scale in the same way. So the flat space contribution defines fully the scaling of the density with respect to h. And what we have now is a setup. We know the matter and density components, and we also have the usual Friedmann equations. We can study how these behave. Once again, the initial setup does not give a pressure plus density equal to 0 as in the usual de Sitter case. We need to modify our expressions a bit. And what is actually happening is that these thermal parts, these thermal components should stay constant in time. So we have some energy inflow from the horizon. And taking everything into account, one can finally solve for h, the Friedmann equations, and get this expression here. And from that, we can estimate the quantum breaking time, which actually is defined as the time where this h gets the value h0/2. So it's some kind of de Sitter half-life time, or however you want to call it, decay time. And this estimation gives the following expression for the quantum break time. And then this is the same expression as with value at all. And this would give them no internal inflation type bound for the scalar potential. Now we should generalize that to strings. To do a direct generalization, direct stringy computation, we would need to trace over states in a stringy Hilbert space, and I don't think this is something that's easy to do. So we assume once again that if we did this tracing over, we could get thermal contributions for the energy momentum tensor, and in flat space. Once again, it's the same as before, direct generalization. And we know now that the free energy for a string gas in n dimensions is the same as the vacuum energy of a string theory in n+1 dimensions, where one dimension has been compactified on a time circle, Euclidean quick rotated time circle. And there is a generic expression for the free energy of a string at the temperature T in n-flat dimensions, which is the following. And here the partition function z string runs over pretty much string states, like internal states, KK modes for the compactification over internal dimensions, and winding modes. And we also have even oscillator modes. Everything pretty much is in here apart from the integration over momenta, which has already been carried out. And now we want to write down an expression for this thermal string partition function. This is something that has been worked out in detail in the past. And there is a recipe that ensures that the final thermal partition function is modular invariant and has correct properties like bosons coupling to integer modes and fermions coupling to half integer modes. And this happens by first considering a winding Scherk-Schwarz orbifold, where here we have a winding shift, and this here is the fermion spacetime fermion number, and then also taking into account modular invariance. And the final thing, after taking into account also the twisted sector, would be a thermal partition function of this form. An example of this type would be the type 2b finite temperature partition function, which has this usual form, this extended form, let's say, and you can see that in the first two parentheses, one has the usual type 2b contributions, but then there are other things coming from the twisted sector. And what is actually interesting is that this third term here, which contains winding modes, becomes tachyonic for a temperature above this critical value here, which is actually the hagedron temperature of the string. And as was already claimed or argued in the 80s by Attic and Witten, this winding mode becoming tachyonic is not, and this temperature is not a limiting temperature of for string theory as was initially believed, but is, on the other hand, indicates a phase transition. And beyond this hagedron temperature, we have drastic reductions of degrees of freedom, and now the free energy density scales quadratically with T instead of the usual field theoretic expectation like T to the n, where n the number of dimensions of the effective field theory or string theory. And of course, since we have the free energy density, we can compute density and pressure with the usual string thermodynamic expressions. And we get two distinct expressions. The first one is for low temperatures, which is below this hagedron temperature, where what is relevant is mostly the light KK modes. And the equation of state here is the usual radiation equation of state, and the scaling of the density is the usual T to the n or H to the n. I will use them interchangeably, even though there are some factors of 2 pi, and there is a factor of 2 pi distinguishing them, but I'm not taking these factors into account right now. And the other regime, temperature regime, that is probably more interesting is the high temperature regime, which is beyond the Hagedorn transition, we assume now that there is some kind of tachyon-free description, and there what becomes very relevant is the light winding modes and not the KK modes anymore. And extrapolating this thermal partition function as Adigan Witten did shows this universal quadratic behavior. And if you actually do that for keeping only the very light winding modes for supergravity theory, you can explicitly see that this quadratic behavior is verified in several dimensions. Here we have worked out 4 up to 7. And the equation of state is pretty much of the same for where n equals 1. And everything that I've just mentioned here is summed up in this pictorial form. So let me proceed. And now we try to extract the bounds for the potential using this age scaling of the energy. First of all, we need to, it's very similar to what was done in the field theory case, but now we need to pay attention to a few things. First of all, that the Planck mass is not fundamental, but is defined, is derivative, let's say, of the string mass, which is the fundamental one. Second, we expect to have some kind of higher order derivative corrections in the Friedmann equations, but I will assume these are negligible since we are working in a regime where H is much smaller than the string mass. And also in Einstein frame and large volumes, the KK Kaluch supply modes from the internal compactification play an important role, and the energy density pickups an additional multiplicative volume factor. So the quantum break time is identical as before, with a difference of this extra V factor in the denominator, and everything can be expressed in terms of M string and GS. And applying the same method as before, one gets the bound from the quantum breaking censorship, and this is that V prime over V has to be greater than GS times H over MS to the power n minus 2 over 2. And now a few comments are in place. First of all, this has the usual functional form as the no internal inflation bound, since we know that H scales like V squared, square root of V, sorry. And also this is effectively a stronger bound than the usual bound we had due to the factor of V. And here we see that instead of the Planck scale, the string scale arises, but this is something, let's say, to be expected since the string scale is more fundamental than the Planck scale as a limiting, as a cutoff of where effective theory should stop working, let's say, in the framework of supergravity or the Swampland. And the other regime was the high temperature regime. Now, there is a small disclaimer that the corrections in the Friedmann equations and the gravitational action could be now of order 1, since we are treating, we are going to high temperatures beyond the string mass. But since we don't know what are the actual degrees of freedom in this regime, we still assume that the leading order in the Friedmann equations would still hold. And this could be related to the fact that the theory may be beyond the temperature. The higher temperature could be a topological theory or a theory with some kind of enhanced symmetries, and this could save these Friedmann equations. But this is something that is speculative at this point. And then we make use of the different scaling. The Hubble parameter now scales like that. The quantum break time has this exact form that was required to get a V-independent right-hand side in the quantum breaking bound. So what we get is V prime over V has to be greater or equal than G string. Now, okay, one could say this is not an order 1 positive constant. Okay, at least it's positive. And the other thing is that in order to do that, we use this approximation for the free energy that was the first loop free energy approximation. So maybe this is where the GS factor sneaked in. So it could be an artifact of our assumptions and disappear in different cases, but an explicit calculation would be required in order to have an actual answer to this thing. And okay, then I hope I have convinced you that there is enough motivation to consider this link by raising the temperature of the string theory. And still a better understanding of the high temperature regime is required in order to draw any definite conclusions. It would be very interesting to have an explicit verification of the T-squared behavior. The other thing that would provide a lot of support to our view is to uncover some explicit string model where only TCC is verified at 0 temperature, let's say. All right, this is all I had to say. Thanks a lot. I think I'm right on time.
Great. Thank you, Andriana, for your very nice talk. Let us all use our clap emojis. Are there any questions? While we wait, I think I have one. So I was a little confused about the low temperature regime. You made a point of emphasizing that there was this this factor that modified the bound as compared to the scalar case. But I would have expected that at very low temperatures, the string is essentially just its 0 mode. And,
yes, we
its
don't go to very,
states.
very.
So this is moderate temperature.
Yes, it's not going to 0 temperatures, let's say explicitly. We have a bound that is pretty much related to the masses of the fundamental modes that arise in our spectrum. So we are beyond this kind of mass. It's some kind of intermediate temperature regime. And below that, instead of this h to the n scaling, we have an exponential suppression, actually.
Sorry, you have an exponential suppression in what?
In the scaling of rho. It's scales like e to the minus m over h, let's say, where m are masses or whatever. Modes, KK mode numbers or.
Okay, well, if there are no other questions, let us all thank Andriana again. And with that, let's thank both of our speakers. Next week, we will not be meeting, but the following week we will. And so I hope to see everyone back here again. So.